So today we're going to look at an old servotube STA2504S. It's a tubular linear motor, and there's in the rod are pairs of magnets. So north and a south magnet, 51.2 millimeters for each pair of magnets. And of course the coil, and there's two Hall sensors, which are used for, they're analog Hall sensors used for commutation and then interpolation. So the feedback connected to the drive, sine plus and minus, cosine plus and minus, +5 and ground. Motor power UVW. I'm just using a 24 volt supply. You could use 48 with this ACJ. Another ACJ could do 80 volts for higher speed. This is the new ACJ with the ARM processor that can do sine cosine. So we'll take a look at the specification for the Dunkermotren servotube. Used to be the Copley servotube, but sold it to Dunker. And we have the specification for the 2504. It's the S or series winding, 312 for peak, continuous force, 42.5. Got some peak current, 20 amps. That's considerably higher than the rated current. Parallel winding would, of course, be more current, but looks like less force, peak force, yeah. And the pitch again, 51.2. You got your back EMF constant, your torque constant, your inductance, your resistance, all the good stuff here. And thermal specifications, dimensions. The rods come in different lengths. The coil is always the same length. So there's the UVW, and for the Halls, for the Halls, it's a 1 volt peak to peak sine and cosine, kind of like a sine cosine encoder, but it's Halls. And some details about the innards of the motor there. You can see sine cosine differential, apply ground, this temperature sensor too. There's a shield for the motor case. That's always a good thing to connect up. There's some colored wires for the flying leads. Oh, look, the Zenus XTL-S. Okay, the XTL REV02 is replacing the -S, and I'm using the ACJ REV02 or REV01. Black wires labeled 1, 2, 3. That's always fun. You got a UVW, and green is ground, yellow is +5. You got your blue, red, and your white, brown for the differential pair for sine cosine, and ordering number. Now for the ACJ, we're going to take a look at the, there's the frame ground for the motor case. There's UVW. You've got the feedback connector, differential sine cosines, differential cosine, signal ground, and a frame ground for the shield for the feedback, a motor temp in with respect to ground. If you hook up the motor temperature sensor, I'll just set the current limits to protect the motor. So let's take a look at the configuration. So the basic setup would be a brushless linear motor, no brake, although there is a linear brake option for this motor. Kind of weird, but you gotta, like Chinese handcuffs, you gotta go up to release it, and then when you turn the voltage off, it grabs the shaft. Analog Hall type, low frequency analog, so that's the selection for the feedback. So commutation and interpolation. It's a 51.2 millimeter. I got a 12-bit AtoD in this ACJ, which is fine. I set 5,120 interpolation counts per pair of magnets, and I get a 10 micron. With a 16-bit, you can go up to 51,200 and get your 1 micron resolution. And with a 16-bit AtoD in like an APV, you can get some really good repeatability. That's not accuracy. If there's a break, you can come to a controlled stop, and this is just in a CAN mode. Nice safe mode, can't be enabled on power up. So I enter the data for the motor. I'm not going to go this fast. I've only got 24 volt supply, so I'm going to keep the speeds under 1,000 RPM. I think on 24 volts with 6 ohms and a few amps, you're going to use up your 24 volt supply pretty quick. So 48 might be a little bit better for the 2504. And you press calculate, you get the initial tuning parameters, and the current limits are all set. Check the bandwidth. Should get about a kilohertz of current loop bandwidth. I think 500 to 800 hertz is sufficient. It's a linear motor, so you don't have to go through the electrical cycles so fast. So this is good. Nice round values. You can see that I did the tuning there. On the velocity limit, on the V-loop screen, you got to make sure this is larger than anything you want to do. And there's some gains for VP and VI. Again, tuned by a human, so they're nice round numbers. And the position loop, I cranked the gain up from the default, a little bit more stiffness. And tracking window defaults, this all looks good. And we'll take a look at the phasing, motor phasing angle. And I'm going to give it a little bit more current, maybe an amp. And I'm going to go forward. If it's going in the direction I want to be forward, I'm good. I don't have to invert the motor. What you're looking for here after forward and reverse is that you don't have any wicked lag or wicked lead of the red feedback. If you had an offset in phase, you would see a wicked lead and a wicked lag. But this came out pretty good. I had to invert the feedback because when I go forward, counts have to go up. And when I was doing this, I didn't hook up one of the motor wires, so I saw no current in the W. So that was a good indication. So good tool for troubleshooting. So the phase looks good. I can proceed with the tuning. Again, the current loop gets tuned, commanded, and actual. Looked a little buzzy with a little ringy. Cut the gain in half, and we could do some more integral. But when the integral is too high, get some integral wind up. It's a little bump up here. It seemed like I had a little bit of over integration here. There's a little bit of a wind up. I don't know. I don't need wicked high bandwidth, so this should be sufficient. Then for the velocity loop, auto setup checkbox. Make sure the motor's in the middle because it's going to go bang, bang, back and forth. I knocked the acceleration limits down. They were 5 times bigger from the calculated value. But this should still be some pretty good acceleration. I like to monitor the actual current with this. So bang, bang, back and forth, forward and reverse 5 times a second. You can see the currents getting about an amp. I got a little bit of a ring here, but I'm getting the speed. The commanded and actual looks good. I guess if there's no integration, maybe you don't quite get the speed, and if the gain's too low, you might not get so much characteristic bounce out of it. But yeah, kind of droopy, not so stiff. If the gain's too high, you're going to break into oscillations. So there it is. You can hear it. So too much gain, oscillations. 400 seemed a little bit ringy to me, so I'm just going to knock it down. 300, get rid of some of that ring. And then for integration, maybe 30 is okay. You can come back to this when you tune the position loop. But too much integration will cause ringing and will overshoot. So we'll see that better when we do position moves. I don't use the function generator for that. I'm going to move this towards the negative side a little bit. So then I can make a move, trapezoidal move. There's some, I'm going to limit the speed here. Auto setup checkbox. This is a pair of magnets, 51.2 millimeters, or that many tens of microns. And let's look at the current, actual current. I'll monitor the voltage, bus voltage, and voltage, terminal servo, and I'll look for the voltage warning because I ran out of voltage, and bang, made the move. I can make a negative move, repeat and reverse from this position. Yeah, looks like a little bit of integrator wind up there, so I'm just going to knock this back down. So it didn't settle very good, and we'll watch it go back and forth. So yeah, the integral pulls us in. We can try to go faster, and this may hit a voltage limit because it's IR drop plus, yeah, so I'm constantly voltage limited, and you can see the error starts to exponentially increase. That's not a good speed for this voltage. And I use some current, plus or minus a couple amps, so you could have, without the mass, considerably higher speed. A little bit of voltage limit's okay. It's not causing the change to the error, but I'm going to knock it down to 500 millimeters per second, and pretty stiff. If it's a point-to-point move, you could ease up on the VFF, velocity feed forward 8192. That just allows some error while you're moving. With the default gains, it might not be so stiff. Yeah, see the error while you're moving, but it settles nicely. And let's crank up the proportional gain here. So every time I crank up the proportional gain, I get more stiffness, although it could get a little buzzy. So it's a little crunchy and a little grindy, but the error comes down. Oh, that's a little too much there. Let's cut it in half. But it gives for some really good stiffness. It's a very powerful linear motor. And you can save the scope trace if you want to an SCO file. Save to flash after you're done configuring, and save to a CCX file. And we'll call it, I don't know, Dunker? Here's a Dunker. STA2504S with a ACJ REV01 ARM SIN COS. All right, so that's it for today. Thanks for watching.